In this video, what I want to talk about are the matrix elements of the linear operator. Okay, so to do this, I'm going to go back to the analogy of column vectors and row vectors. So if our ket, this vector v, is a column vector of n elements, and our bra is a row vector of n elements, like so. So those two dimensions of both of those vectors, the column vector and the row vector, match. If I'm going to be operating, so say I want to operate with the operator omega on the vector v, then what I would want to do is to basically get back with this operation here a column vector of dimension n. So if I take my operator omega and then I multiply it or operate onto the vector v, then the dimensions have to match such that I'm still going to get a column vector of n, because when I eventually take the inner product of v on this, so basically the inner product of v on the transformation of v by omega, then I still want a single number. So basically, when I multiply my row vector of dimension n on my transform vector of dimension n, then a row times a column is going to give you a single number. So that means omega is going to produce an n by n, or be represented by an n by n matrix. So there are n squared elements inside this matrix, which I'm calling omega. Now, if I think about this, I can apply this to a set of basis vectors. And so I take my operation of omega times that column vector v. I can write v as the sum of a basis I so I have my basis vectors represented by the I kets, and then I have the little v coefficients in front of it. So now if I move this operator omega inside the summation, I have the sum of vi omega times the basis states I. And when I do that, I'm basically transforming into a new basis. So now what I can do is I can project that operation of omega on v onto another basis, j. So I can take the projection of j after I operate omega on v, and what I get is the sum of vi, the coefficients, the inner product of j on omega, which is now operating on the basis states I. And when I do that, I basically get a number. I now have an inner product of j operating on the transformed basis I. So what I get is coefficients vi times now coefficients, which I'm going to call omega ij. So these omega ij are called the matrix elements. of the operator omega. So now you can think of them as the elements of this n by n matrix that we have for the operator omega. Okay. So if I think about it in terms of matrix, if I want to draw it as a really big matrix, then what I'm really doing here is creating these new elements V prime by multiplying and I'm running out of room here. All these matrix elements times the original vector v1, v2, vn. So I'm basically taking my original column vector v right here, and I'm operating with this matrix, n by n matrix, where I've now got all of these matrix elements, basically the projections of direction j on the new transformed basis I, and creating a new vector v prime out of that. So this is a basis transformation. So I'm transforming from basically the vector from what originally the initial state v into the new state v prime. So again, I mean, this is a lot like rotations in classical mechanics, where if I have a vector v, which is, I could write it as 1, 2, and 3. So I'm kind of mixing notation now. I'm mixing my ket notation with my row vector notation, but hopefully in the end it won't really matter. But basically I can now apply rotations to the whole vector, this vector which lists these different vectors. So if I apply a rotation about the x-axis around 1, it doesn't change. A rotation of the x-axis on the x-axis is just the identity. Rotation, a 90-degree rotation around the x-axis on the y-axis gives me the z-axis, and a rotation of a 90-degree rotation around the x-axis on the z-axis gives me basically the negative y direction from there. So if I instead now I wanted to write this out as a very compact vector, so the vector v prime is equal to my 90-degree rotation about the x-axis on v, I could write it out as, here's my rotation matrix. So I'm multiplying this 3 by 3 matrix on my original vector, which is just x, y, and z. And then what I get is the result I have above. X doesn't change, y becomes z, and z becomes negative y.